Good morning, everybody. My name is Moulfi Bouchra. I am doctoral student in University Belhaj Bouchaib of Anti-Motion Assistant Laboratory from Algeria. Today, I'm going to speak to you my work of Terahertz rectangular antenna for biomedical application. Let's move to the plane of presentation. First, we will start by introduction and the objective. Then we will talk about proposed antenna design. Then we will explain simulation and the result with different types of substrate material. Finally, we will finish it by conclusion. Telemedicine is this plane of medicine that uses information and communication technology to provide treatment remotely. People can receive health care remotely without having to physically visit the medical center. Antennas are essential in wireless body area network, as they enable wireless connection between monitoring equipment, medical instruments, and sensors implanted in the patient's body. They can be in body, on body, or off body. In medical technology, antennas require a reliable communication network with constrained bandwidth to transmit real-time data without interfering with other networks. They also require minimal energy consumption to extend the battery life and are remotely designed for short-distance communication with low gain due to their resistance to human interference. To meet this requirement, Terahertz 0.1 to 10 Terahertz band of the so-called far-infrared zone is being used to provide an antenna with a compatible size of nanometric order and low energy consumption with several advantages of note. 1. Resolution imaging. Terahertz imaging technology uses electromagnetic wave with a wavelength in terahertz region to produce picture of biological tissue. The wavelength of terahertz wave, which is shorter than that of microwave but longer than that of infrared wave, able them to penetrate deeper into biological tissue without damaging cell, helping doctors to identify illness early and more precisely. 2. Possible health risk. The terahertz band is considered to safe from human use due to its non-ionizing nature, unlike X-ray and ionizing radiation. DNA can be damaged by X-ray, potentially increasing the risk of cancer. Terahertz waves on the other band are non-ionizing electromagnetic waves that do not bring chemical bond in molecule like DNA. It makes them ideal for healthcare application, enabling non-invasive imaging methods that are safe for patients. 3. Used in-body scanner. Terahertz wave can penetrate the skin and detect change in the density of physical tissue, assisting in the diagnostic of lesions or disorder. Terahertz body scanner offer advantage over typical medical scanner in that they are non-invasive and not exposed to ionizing radiation. The objective. In this work, we will design a rectangular wireless body area network nano antenna in the frequency band 1.48 to 1.45 terahertz. The different substrate type Erlon AD 2050 and Roger 303 and Roger 303 polyimide and gold as conductive material for body application. The proposed antenna design. A nano-rectangular slotted patch antenna was designed using CST software filed by microscript line, which 50 ohm impedance. The ground plane and the patch are simulated using gold material, which 6 micrometer thickness, while the electric substrate made is Avalon with 5 micrometer thickness, shown in figure 2. To simulation result noted by 1 return loss. We can see that the proposed antenna have a return loss of minus 44 with 44 with 1.48 terahertz frequency. 2 in VSWR. We can see that the VSWR of proposed antenna are less than 2 in resonance frequency. We can see in figure 5 that the gain of proposed antenna are 5.32 in proposed resonance frequency. Simulation and result with different type of substrate material. The substrate used for the patch antenna significantly impacts its performance. In microwave band, low constant dielectric substrates are preferred due to their larger effective bandwidth, high radiation efficacy, and wide bandwidth. For the best choice of the optical band, wireless body area network 0.1 to 10 terahertz, we will simulate our proposed rectangular antenna with other substrate material. Roger 403C, Roger 303 polyimide and polyimide. Simulation results are presented for comparison in figure 6, 7, and 8. We can see in figure 7 a return loss of our proposed nano-rectangular antenna with different type of substrate material. We can see that a substrate Roger 303 have best return loss of minus 42 at 1.5 terahertz frequency. We can see in figure 8 that all proposed antenna with different substrate material have a return loss less than 2, so our proposed antenna are best adaptation. Figure 8 presented a polar gain of proposed nano-rectangular antenna with different type of substrate material. Figure 10 presented a 3D gain of proposed nano-rectangular antenna with different type of substrate. A with the substrate Roger 403, B Roger 3003, and polyimide. We can see that the best result of gain have with the Roger 3003. 3003. The optical band, which includes visible high and length frequency, is a range of wavelength in electromagnetic spectrum. This work represents a nano-rectangular patch antenna design using slide technique for terahertz electromagnetic wave. The antenna's small size, 55 micrometer, allow for easy integration in various devices and a real-time reference. The antenna achieved excellent results with coefficient reflection of 34, 36, minus 36, minus 23, and minus 42, and higher gain of 5.52, 5.69, 6.55 dB, and 5.48 dB at frequency of 1.48, 1.52, 1.55, and 1.5 terahertz, which use different substrate material, polyimide and Avalon polyimide and Roger 3003 and 403C, respectively. The terahertz antenna offers an excellent characteristic and can be used in various applications. Thank you for your warning.